I am glad to make this presentation at ICML 2024. The title of our paper is Scalable Multiple Kernel Clustering, Learning Clustering Structure from Expectation. The purpose of machine learning algorithms is to learn the statistical regularities of data distributions from empirical data. However, due to noise interference in empirical data, biases often arise. In single-view learning tasks, a basic assumption is the data is generated from a Gaussian distribution. As shown in Assumption 1, every point is an addition of the signal y and the noise epsilon. Epsilon obeys a Gaussian distribution. The motivation for this paper is based on the above assumption. If each view's data generation model is as described above, we aim to design a multi-view clustering algorithm to explore the clustering structure of the data from all base views. We assume that there are multiple views which have the same clustering structure. The clustering task is to find the unified clustering result from these views. For each view, we suppose that it is generated by a signal pulse of Gaussian noise. The formal descriptions are shown in Assumption 2. Under Assumption 2, we derived Theorem 1. This theorem formulates the expected kernel matrix when the dataset meets our assumption. It is easy to see that the expected kernel matrix is also a kernel matrix. For two different clusters, P and Q, if their clustering centroids are well separated, then the expected kernel matrix can approach to a low-rank block matrix with rank K. In this sense, the expected kernel matrix has an explicit clustering structure. We then give Theorem 2. It describes the distance between the empirical kernel matrix and its expected. This theorem shows that the normalized kernel matrix can converge to its expectation as the dimension tends to infinity. According to Theorem 1, we know that the expected kernel matrix exhibits a noiseless quality and manifests a distinct clustering structure. However, we cannot directly obtain the expected kernel matrix. As stated in Theorem 2, the empirical kernel matrix closely approximates its expectation. Thus, we can employ kernel principal component analysis to denoise the empirical kernel matrix, as shown in Equation 3. The problem in Equation 3 is equivalent to the problem in Equation 4. Finally, Equation 4 can be converted to Equation 5. To unify the clustering information of all views, we aim to minimize the distance between the ~kv and a rank K consensus kernel matrix K star. That is the optimization problem in Equation 6. Combining all, we have Equation 7. However, solving the problem in Equation 7 will cost a large amount of time due to the eigen decompositions of the n times n matrices. Inspired by the anchor-based methods, we can effectively reveal the clustering structure from a small portion of the whole kernel matrix. For each view, we can randomly select S anchors. Then, we construct base kernel similarity matrix G versus whose size is n times S. By replacing KV with GV, we can obtain a scalable multiple kernel clustering method, as shown in Equation 8. We can alternately optimize the ~GV and G star in Equation 8 by the following procedures. With a fixed G star, the problem can be converted to Equation 9. It is the best rank K approximation problem. With the fixed ~GV, the optimization problem is equivalent to Equation 12. It is also the best rank K approximation problem. We first analyze the storage and computational complexity of our algorithm. First, storing V-base kernel similarity matrices occupies O(VSN) space. Second, the time consumed by solving the problems in Equation 12 and Equation 10 is linear with the sample number. Thus, the proposed method can handle large-scale datasets. When the inputs of the proposed algorithm are V-whole base kernel matrices, we denote the output as K star. We also give the upper bound of the distance between K star and G star as shown in the theorem. By the above theorem, we can obtain corollary 1. The first k singular vectors of k star and G star can be the input of standard k, means to obtain the final clustering results. Corollary 1 shows that the G star can well approximate the k star with regard to clustering performance. We conduct experiments to test the clustering performance of our method. We select 6 benchmark multiple kernel datasets, and their detailed information is in the table. As seen in the comparison experiments, our method obtains the best performance. It shows the effectiveness of our method. We also conduct experiments to test the running time and clustering performance of our method with different anchor numbers. As seen from the 2 subfigures on the left, the derived theoretical result in corollary 1 is verified in numerical experiments. The subfigures in the middle show that the running time of our algorithm increases when the anchor number becomes large. The subfigures on the right show the values of NMI with different anchor numbers. It can be observed that only a few anchors can obtain desirable clustering results. Finally, we conduct experiments on large-scale datasets to test the efficiency of our algorithm. These 2 datasets, respectively, have 50,000 and 325,834 sample numbers. In the aspect of execution time, our algorithm can manage all large-scale datasets in the manner of kernel clustering method within hundreds of seconds. It shows the high efficiency of our algorithm in handling large-scale datasets.